Deep beneath the Alaska range, the crust snapped. A magnitude 7.9 earthquake, the largest to strike the North American interior in 150 years, began unzipping the Earth. The rupture tore across glaciers and severed highways moving at supersonic speeds, but directly in its path lay a 4-foot-wide steel artery carrying 17% of the United States' domestic oil production. For decades, engineers had debated this exact scenario. This was the moment that would determine if a billion-dollar engineering gamble would hold, or if the Alaskan wilderness would suffer an unprecedented environmental catastrophe. To understand the scale of this threat, we must look back to the project's chaotic beginnings. In the 1970s, the Trans-Alaska Pipeline was the largest private construction project in history, but it faced a geographic nightmare. To transport crude oil from the frozen reserves of Prudhoe Bay to the shipping terminal in Valdez, the route had to cross the active Denali Fault. Geologist Lloyd Clough was the man responsible for analyzing this risk. His team's assessment was terrifyingly specific. They did not just predict shaking, they predicted a violent displacement of the Earth itself. Clough calculated that the fault could slip 20 feet horizontally and 5 feet vertically in a single event. Any standard pipeline, buried or fixed rigidly to the ground, would shear instantly and pump millions of gallons of hot crude into the pristine watershed. The proposal to build for this maximum credible event met fire resistance. Project managers and accountants viewed Clough's specifications as financial madness. They labeled the precautions gold plating, spending millions on a defense against a disaster that might not happen for 500 years. The tension between timeline, budget, and safety was palpable, yet the geologists refused to sign off on a design that ignored the fault's potential violence. The compromise was a piece of infrastructure that looked like science fiction. The engineers designed a floating system across the fault zone. They lifted the pipeline out of the ground and set it on H-shaped supports. But the pipe was not bolted down. Instead, it rested on shoes coated with Teflon, the same material used in non-stick frying pans. These shoes sat on extra-wide, 40-foot steel beams, buried deep in the gravel. The physics were counterintuitive. The goal was not to hold the pipe in place, but to let the ground move freely beneath it. If the Earth jerked 20 feet to the north, the Teflon shoes would slide along the beams, allowing the heavy, oil-filled pipe to stay relatively still, isolated from the violence below by a layer of frictionless plastic. It was a brilliant, unproven theory. Once installed, the system sat silent. For 25 years, the beams waited in the cold, the Teflon untouched, as the pressure deep underground slowly built toward the breaking point. The sequence began on the Susitana Glacier Thrust Fault, a hidden structure south of the main danger zone. The initial break was vertical, shoving a massive block of the Alaska Range upward, but the energy did not stop there. It transferred instantly to the Denali Fault, the primary strike-slip boundary, creating a complex, multi-stage rupture. The Earth began to unzip from west to east across the mountains. The rupture accelerated until it achieved super shear velocity, a rare seismic phenomenon where the breaking fault moves faster than the shear waves it generates. It was, effectively, a sonic boom traveling through solid rock at over 7,000 miles per hour, tearing a physical scar across the wilderness that would remain visible for years. The scale of the destruction was absolute. The tear extended for 209 miles, slicing through glaciers and severing valleys. When the fracture hit the Talk Cutoff Highway, it did not just crack the pavement. It sheared the road completely, creating a lateral offset of nearly 23 feet. One lane of traffic was suddenly sitting 8 yards away from where it had been a second before. The release of energy was staggering. This was a magnitude 7.9 event, 30 times more powerful than the earthquake that collapsed freeways in Oakland in 1989. and comparable in raw power to the 1906 disaster that leveled San Francisco. Had this rupture occurred in an urban center, the devastation would have been total, and instead, it expended its violence on the ice and rock of the interior. The shockwaves were so intense that they ignored the boundaries of the state. The ground motion rolled south, traversing the Canadian Shield and the continental United States. In Seattle, the waves hit Lake Union with enough force to damage houseboats. Even further away, in the bayous of Louisiana and the swimming pools of Texas, the water began to slosh violently. A phenomenon known as a seiche, agitated by the low-frequency energy arriving from 3,000 miles to the north. Residents in the southern states watched their pools overflow with no sensation of the ground moving, unaware they were witnessing the distant echo of an Alaskan catastrophe. But the most critical impact point was much closer to the epicenter. The super shear rupture was racing directly toward milepost 589. This was the exact coordinate where the pipeline crossed the fault zone. For 25 years, the structure had stood static, holding its cargo of hot, crude oil above the frozen ground and the fragile permafrost. Now the theoretical limit was becoming a physical reality. The fault line approached the crossing at supersonic speed, carrying enough energy to snap the 4-foot steel pipe like a twig. If the steel buckled, the resulting spill would destroy the local ecosystem. As the rupture front arrived, the ground beneath the support beams did not just vibrate. It moved exactly as Lloyd Clough and his team had predicted it would 3 decades prior. The Earth lurched sideways, subjecting the billion-dollar engineering experiment to the ultimate stress test. At milepost 589, the theory finally faced the brute physics of a magnitude 7.9 event. In less than a minute, the fault severed the ground beneath the pipeline. The earth on one side of the crossing surged roughly 18 feet horizontally and nearly 3 feet vertically. If the pipe had been buried or even fixed rigidly to standard supports, the metal would have torn instantly, spraying crude oil across the tundra. Instead, the slider system engaged. As the gravel pad and steel beams were thrown violently sideways, the heavy pipeline held its inertia. The Teflon shoes skidded across the long horizontal beams, screeching against the steel, but refusing to lock. The pipe flexed, bowing under the immense compression like a loaded spring, but the weld seams held. For the engineers analyzing the data later, it was the validation of a lifetime. When the shaking stopped and the dust settled, inspection crews arrived to a scene of chaotic geometry. The landscape was offset, the road was severed, and the pipeline looked like it had been battered by a giant. Insulation was scattered across the snow like confetti. Witnesses described the damage as if the Hulk had twisted the steel shoes apart. Several vertical support members had been knocked out completely or bent by the violent contact. In sections, the 4-foot-wide pipe was hanging unsupported in the air, suspended only by its own structural tension. But the most chilling detail was found on the slider beams themselves. The Teflon shoes sat precariously close to the edge of the steel supports. In the 1970s, Lloyd Clough and his team had fought for a design that accommodated 20 feet of slip. The Earth had moved 18 feet. The system had used up almost every inch of its safety margin. One engineer later compared it to kicking a field goal from the 50-yard line against the wind. They had aimed for a specific window of movement, and the fault had hit exactly where they predicted. Had the fault slipped just a few feet further, or had the engineers capitulated to budget cuts that demanded shorter beams, the pipe would have dropped off the supports, sheared against the frozen ground, and unleashed an environmental disaster. The operational response was immediate. The automated systems detected the seismic waves and slammed the remote gate valves shut. For 66 hours, the flow of oil stopped. This created a new, silent ticking clock. In the Alaskan interior, static oil cools rapidly. If the crude temperature dropped too low, the oil would undergo waxing, turning into a thick gel that is impossible to pump. If that happened, the pipeline would not just be broken, it would be ruined. Crews raced against the thermal drop, calling in every available timber from the north slope to shore up the damaged supports. They built giant wooden cribbing to stabilize the bowing pipe while running integrity tests on the stressed steel. They checked for hairline fractures and seal failures. The results were conclusive. Despite the violence, the bending, and the near collapse of the supports, the containment remained perfect. Not a single drop of oil had spilled at the fault crossing. The survival of the Trans-Alaska Pipeline proved that critical infrastructure can survive extreme seismic violence if we respect the geology during the design phase. It transformed earthquake engineering from a theoretical gamble into a proven science, demonstrating that while we cannot stop the Earth from moving, we can choose whether we break with it. Subscribe to understand the engineering behind the world's biggest disasters.